Hey, how are you? Um, Hi, I'm Mark. And this is not the second time I've done this entire show all the way through. It's not. And it's not because I've just spent the last 3 hours playing Metal Gear Solid 5. It's not. If you think that, I am deeply offended that you even have the audacity to know me that well. Just anyway. So yeah, I did it. Actually, I did it once. I was like, man, it's because I looked at the clock and I was like, oh, crap, 4 o'clock. So I jumped in, thought I'll just blow through it. I can't blow through this stuff, man. I actually need time to prep and think about what I'm going to say, even though I don't know what the words are coming out of my mouth right now, as you can tell by that last sentence. But as far as like what I'm going to say, again, you can't see white on the screen. I don't know why I keep showing it. But I don't know. I'm trying not to get in the habit of doing these again. I mean, I'm lucky in the fact that when I do these live on the Google Hangout, I can't say Google, and Google and Hangout, that there's nobody watching all the crap on Google Hangout. Oh man, I'm glad public television has still got a place. God bless you, Pro Ultra, wherever you may be. But I don't want to get in the habit of doing that. All right. But this one I thought I'd go through again. I don't know why I'm saying this. You have no idea, unless I hadn't said it. I could have just started over and went, "Hi, how you doing? Let's go on the gym." But no, I decided to confess my sins to you, the viewer, who was nice enough to watch this, or confused enough, or I don't know, however you're feeling. But for the general one, folks, hey, general one, folks, you guys, I thought I'd talk a little bit about some Ionic covalent stuff. We talked about naming last season, and so that's still there. And you can also see the video that I got on my other website, Gen Chem Concepts, because I ended up turning, gosh, I think that's the way it was. I turned those slides actually into an actual honest to God well-produced video, semi-well-produced, with a script and everything. And yeah, I've done a few extra videos if you go to the website that's no longer just me with a notepad, because I'm actually doing some more for the Kindle edition of my Gen Chem textbook. And again, I don't mean to plug it every week, but I really should, because I should self-promote a little more. I'm kind of proud of it. But yeah, the Kindle version actually has all the Gen Chem Concepts videos built in. And when I did that, I decided to add some new ones. And I'm currently doing that for volume 2, if I can stay focused. No, if I can just stop making more, because I keep thinking, all right, I make this one, I'm done. It's like, no, I want to do one for nuclear chem now. Oh, I might do another one for nuclear chem. And now that I'm up for this show, I actually prep slides for you guys for General 2, and I'm thinking, oh, that might make a pretty good video, but I'm in no rush. Obviously, right? I mean, look how long it took me to get to General 1. Hey, let's talk a little bit about ionic and covalent compounds. What do you say? All right. So for you guys, first off, we'll say a little bit about ionic compounds. And the first thing to remember is that they don't actually exist as molecules. You don't really have an ionic molecule. Table salt, for example, is an ionic compound. It's not made up of table salt molecules. What's actually going on is they exist as an almost infinite 3D wall of ions, basically the whole life of the crystal. You kind of know what I mean by infinite. That we call a crystal lattice. And they're held together by electrostatic forces, which is a fancy way to say opposite charges attract. So, for example, the sodium and chlorine in your table salt, again, no table salt molecule. What you actually have is this crystal lattice, kind of like bricks in a wall, where every sodium ion brick is surrounded by 6 chlorine ions, the 4 that you see here, plus 1 in the front, 1 in the back. And chlorine's the same way. It's surrounded by a a bunch of the other ion. So you have this big 3D wall that extends in all dimensions throughout the life of your salt crystal. Should note that they're not always 6 and 6, 6 of one around 6 of the other. It depends on the size of the two ions and their charges, how they stack, but this idea of a crystal lattice is always true. So as far as writing formulas, since there aren't molecules, it's hard to write a molecular formula. So instead we do what we call an empirical formula, which is kind of an offshoot of the molecular formula. And it shows you the simplest ratio of cation to anion. And typically the way we do it is we write the cation first, anion second. And in most cases, that's going to mean the metal first, non-metal second. Because a lot of times in Gen Chem, we work with what we call binary compounds, which are compounds of just two types of atoms. If it's ionic, the cation is probably going to be a metal. The anion is probably going to be the non-metal or a non-metal. That's kind of a really broad general rule, but it's general chem, so it works good enough. Transition metal areas has a few exceptions to that metal equals ionic rule, but it's good enough for general. So either way, the cation's first, anion second, and your net charge is always going to be 0. You should always have as much positive charge as you have negative charge. So it's charge neutral overall. So the table salt crystal lattice, no matter how big your crystal lattice is, you're always going to have 1 sodium for every 1 chloride. So we write the formula NaCl. And again, it's charge neutral overall when it's 1 to 1. And as another example, let's say you're looking at aluminum and fluorine. Aluminum is in group 3, so most group 3 elements form +3 ions. Because remember, for groups 1, 2, and 3A in the main group, group number is usually the charge. For groups 5, 6, and 7, it's usually group number -8. So fluorine and all the other halogens, they're usually -1, 7 minus 8. So with this example, you can probably look at it and tell that you need 3 fluorines for every 1 aluminum to give you a neutral compound overall. It's not easy to do with every cation-anion combination. So to cut down on the number of times you have to stare at it and try to do the math in your head, a lot of people use what we call the crossover method, which is just a quickie way to come up with a formula. And the way it works is that whatever the charge of the cation is, that number goes in front of the anion, and vice versa. So with our aluminum fluorine example, that 3 we're going to put in front of fluorine. The 1 we sort of kind of put in front of aluminum because we don't really write 1s. The 1s are implied. And that can give us our formula. Or if you look at titanium and oxygen, oxygen is going to be -2 because it's in group 6 or 6A. I don't say A all the time because I sound Canadian. But titanium, we'd have to tell you that the charge is +4 because titanium is a variable charge element. So again, the 4 goes in front of the oxygen. Oxygen's charge, that 2 goes in front of the titanium, and that gives you Ti2O4. But remember, the empirical formula is the simplest ratio. So a 2 to 4 ratio can be simplified to 1 to 2. And remember, if titanium 4 oxide here is actually ionic, we don't have TiO2 molecules or Ti2O4 molecules. And titanium is still +4. It's just that we're showing that crystal lattice as simply as we can. So no matter how big it is, you're going to have 2 oxygens for every 1 titanium. So if you're dealing with polyatomic ions, like with magnesium and nitrate, to clearly show that you have when you do your crossover method, it goes, 2 in front of nitrate, 1 in front of magnesium. To clearly show that you have 2 nitrates for every 1 magnesium, we're going to, we put the polyatomic ion in parentheses and put the 2 in front on the outside. That way, again, you can clearly see you have 2 of these guys for every 1 of these guys. Although if the subscript is a 1, you don't need the parentheses. So with magnesium and sulfate, we just would write it this way, MgSO4, not with the parentheses. Because believe it or not, the deeper you get into Gen Chem and the more comfortable you are looking at these formulas, with enough practice, you'll be able to look at this formula and say, oh yeah, that's a magnesium sulfate compound. You won't need the parentheses to kind of divide the two. So that's ionic. Covalent, the main difference between ionic and covalent is that the atoms in a covalent compound are sharing electrons. It's not one atom giving electrons outright to another to form ions that come together through opposite charges attract. Can't get that out of my mouth. And this sharing is called a covalent bond, but that's something we usually don't talk about until later on in General 1, unless you're taking an atoms first kind of class, then maybe then. Or you're taking nursing chem or one of the lower level GOB courses. But either way, covalent bonds, that whole talk will come later. For now, just know that instead of they're sharing electrons, they're not forming ions. And with ionic compounds, you remember you can look for a metal. With covalent compounds, they're usually 2 or more nonmetals. And again, in general chem, we usually deal with binary compounds, 2 element types. If those 2 are both nonmetals, they're usually it's usually a covalent compound. If one of the 2 is a metal, then you can assume it's ionic, at least this early on. And as far as another difference between the 2 is that covalent compounds actually do exist as individual molecules. So, table salt, you don't have a table salt molecule, but table sugar, those are made up of sugar molecules that are stacked one on top of the other to give you that sugar crystal. It's actually made up of individual sugar molecules. And since there aren't any charges, you can't do any kind of crossover method stuff. So you can't really predict formulas for covalent compounds like you can ionics. You can pull, a main group metal and a non-metal and predict what its formula can be, like we did before with aluminum and fluorine or sodium and chlorine. But you just can't pick 2 nonmetals and predict their formulas because there's no crossover method. And not only that, those 2 nonmetals are probably going to be able to combine in a couple different ways or more. Nitrogen and oxygen is a good example. Nitrogen and oxygen can combine to form a compound with the formula NO, where you have NO molecules, or you can have NO2 molecules, or N2O4 molecules, or you can have a compound made up of N2O molecules, 2 nitrogens, 1 oxygen, which for all you racing and dentistry fans, that is nitrous. I don't know if it's still used in dentistry or not. I don't know. I'm old. But with the middle 2, here's another difference about ionic and covalent. With their formulas, you don't reduce the formulas of covalent compounds because they're actually, again, individual molecules. So, NO2 is actually made up of NO2 molecules. N2O4 is actually made up of N2O4 molecules. So you don't want to simplify the ratio to confuse one compound with the other. So again, you don't simplify covalent compounds. They're actual true molecular formulas most of the time. So that's a little bit of General 1 for y'all. I need some water first. Excuse me. This show is sponsored by Dickies. Actually, you knew it was there. No, it's not. Please don't take my nickel away, YouTube. You can let the banner go. Although at this point, if you should, you know to X out banners when they come, right? Yeah, probably. Unless it was an ad, one of the skip ad things, then you already skipped it. So, all right. So with General 2, again, we're kind of easing into things until we get to kinetics. So I think pretty much the last main thing to talk about in the solutions chapter, we covered concentrations last time and last semester. I guess we'll just talk a little bit about solubility in general, which means I have gone completely backwards as far as the order of that chapter. That's okay. I'm sort of ending at the beginning. I'm Tarantinoing a bit. But I keep shuffling papers. I only got 2 papers. I don't know why. I keep just shuffling because I'm trying to talk and whatever at the same time. But, and this is actually a good one to talk about with the General 1 Ionic Covalent talk, because the two are kind of related. So, for example, how things dissolve depends on whether it's ionic or covalent. So, ionic compounds, as you learned back in General 1, they dissolve by dissociation. So, sodium chloride, you put it in water, it dissociates into sodium ion and chloride ion. Magnesium nitrate, when it dissolves, it'll dissociate into magnesium ion and nitrate ion. Again, dissociation just means it dissolves into or breaks up into ions. But with covalent compounds, they actually, or usually, they just dissolve into individual molecules because they're made up of individual molecules. Yeah, most of the time. Acids are a notable exception. So this isn't table sugar. It's a simple sugar like glucose. But you know, a sugar, when it dissolves, it will break up into individual sugar molecules that are now floating around in the water. Carbonated beverages have dissolved carbon dioxide that are basically dissolving around in the water. So as far as being able to predict what type of compounds will dissolve in water, because in Gen Chem we still mainly stick with aqueous chemistry. You know, we talked about solubility in General 1, and for the General 1 guys, I think I might talk about that in a couple weeks. I don't think any General 1 guys are hanging around, but maybe you are. We'll talk about that in a couple weeks. For the General 2 guys, if it's been a while since you had General 1, for the most part, if you think back, most of the soluble compounds, they had really small charges, you know, like group 1A, group 2 ions. But yeah, group 1A compounds are very soluble, and most ionic compounds with -1 ions, a lot of those are pretty soluble. So compounds with really small charges, they tend to be pretty soluble, because water being a polar molecule, you know, the way it dissolves by dissociation, these water molecules come in and basically start pulling the little bricks of your crystal lattice apart. And when the charges are fairly low, it's easier to pull those bricks apart. For higher charges, like compounds with -2 or -3 ions in them, those tend to be more difficult to pull apart. So, because again, their charges are really high, they're really attracted to one another, and they're sticking together pretty tight. Again, it's a broad sort of general way to predict things, but this is General Chem. That's what we kind of do in this class, right? With covalent compounds, sort of broad rule that we use is like dissolves like. And what we mean by like, it can mean different things. It could be similar intermolecular forces or polarities, although a lot of times those two are inclusive of one another, or similar polarities. However you like to view it. Like, for example, a lot of people know that oil and water won't mix. That's because, you know, oil is a small polar compound, most oils are very large, non-polar organic compounds. So they're just not similar enough, not alike enough to want to mix. But oil or water and alcohol will mix because alcohols, especially the smaller alcohols like ethanol, drinking alcohol, again, they're very similar sized. Ethanol is a little bit bigger, but you see that oxygen-hydrogen bond on both of them. So their main intermolecular force, they both have hydrogen bonding. So they will mix. Although when you get to larger alcohols, you know, where you have longer or more carbon chains attached, that'll decrease the solubility of your of the compound, because it's becoming too unlike, too different from water to really dissolve. So a couple of other sort of solubility related things that I decided to go ahead and talk about. I usually talk about it when I mention solubility. Is there's a relationship between solubility and a couple of common things. First off, solubility and temperature. Although it does depend on what type of solute you have. If you have a liquid solute or a solid solute, their solubilities will they tend to increase with temperature, because you're adding more energy to the system. You're able to break apart the intermolecular force that's keeping those things together, and you're breaking them apart enough where they will sort of mix with each other, if they will mix, you know, going back to what we talked about previously. But if you have a gaseous solute, it's the opposite. The solubility will decrease, because remember, gases already have the most kinetic energy of our three main phases. So it's actually the water, the solvent's actually kind of holding it back a bit. So the more energy you put into the system, the easier it's going to be for those gases to be able to sort of break free and enter the gas phase. And you see a similar type of trend with solubility and pressure, in that, you know, gases are a little different than the other two. With liquids and solids, you don't really see any large effect when you mess with the pressure. You know, they tend to stay the same. Their solubility stays generally the same, you know, under most pressure or changes in pressure. But with gases, what you tend to see is the solubility will increase as pressure increases. That's why divers have to be careful about the bends, the condition, not the Radiohead album, because as you go to deeper depths, the pressure is greater, and so your the gases in your blood become more soluble. And if you come up to the surface too quickly, they become insoluble too quickly, and they can form bubbles in your bloodstream that can range from painful to fatal, depending on how quickly and how big they form. So with solubility and pressure, there's a guy named Henry that studied this. His last name's Henry, and he came up with what we call Henry's law. I believe his last name is Henry. Most people don't name laws after their first name. It's not Albert's theory of relativity. But Henry's law says that the solubility of a gas is going to equal this constant, which every gas has its own special constant value of this constant, times its pressure or its partial pressure if you have a mixture of gases. Some books, a lot of books use S for solubility, some use C for concentration, some will use M for molarity. But this is how I tend to write it. And some books won't use a H for Henry next to the K. I do, because we talk about another little K in the next chapter, so try not to get those mixed up. So, for example, oxygen in the air is usually 21%. So if you're under 1 atmosphere conditions, the partial pressure of oxygen is going to be around 0.21 atmospheres. So to figure out how soluble oxygen is under normal pressures, you just take its constant 1.3 times 10 to the negative 3 and multiply it by oxygen's pressure, which in this case is 0.21. So you get a solubility of 2.7 times 10 to the negative 4 molar. So that's how soluble you can make oxygen under most conditions. That's the maximum molarity that you can give that solution. All right. So that's it for now. And yeah, I keep thinking, I actually, when I'm doing the off on the other screen, I'm actually still looking at this camera and doing the hand thingies, but I don't know. I gotta find. One day I'm gonna do a little picture here so you can see me the whole time, because I'm a narcissist. No, because I think it might help a little bit. I don't know. We'll see. Last week I tried cutting it off and cutting it back on, and it takes too much time. But thanks for bearing with me. Although depending on when this is in the semester, you just might be desperate enough to be sitting through this. I don't know. Just good luck with whatever test you got, if that's all you're here for. If you're actually watching these sort of week to week, which is really what I'm hoping most people do, then I'll see you next week or whenever, because you're probably not watching this live, and the whole season, it might be out already, but I don't know. So I guess that's it for now. See you guys.